Okay, now we are going to look at another algorithm for deadlock avoidance. This is called the banker's algorithm. So, where did this name come from and in what cases do we use this algorithm? First of all, the name banker's algorithm came because this was used in banks to ensure that cash flow is always there. Like, no matter how many people come and ask for cash to be withdrawn, the banks should have a supply of cash or ATMs, whatever. It was generally used back then in the banker context. The cashier should have cash and should be able to distribute it to multiple customers without, not being able to service someone's request. So, this algorithm was used initially in that context, and then they extended it to operating systems and processors in general. So, it gets the name banker's algorithm. First point. Second point, when do we use this algorithm as opposed to this one? Now, this, if you have visited the segment on deadlock detection, you have probably guessed it by now. The first one, the RAG algorithm, we used it when you have only one instance of each resource type. So, obviously, when you have multiple instances, you need a more formal algorithm, and that is our banker's algorithm. So, now this is going to be very similar to the algorithm we looked at for deadlock detection. So some of the data that we initialize, some of our this algorithm is most of it is going to be very similar. There's very little new content I have to give you here. So it's going, if you watch that segment, this is going to be very easy for you to catch up with. So if you've not visited that segment, I would recommend you visit that first and then come here, because whatever I've spoken about there, I'm not going to touch upon in much detail in this segment, right? So yeah, with that preliminary stuff out of the way, let's proceed. So we will, as usual, we'll first look at the banker's algorithm, and then we will look at an example, and I think that should make things clear. So the algorithm, first, what data are we initializing? Available, this is this is again the same as in your previous algorithm. By the way, for your deadlock detection, the algorithm we looked at is called the safety algorithm. So, because it helped you find a safe sequence, right? So, it's called the safety algorithm. So, henceforth, whenever I use the term safety algorithm, please know that I'm talking about the this algorithm which we looked at for deadlock detection, and it comes in here also, as you see. Okay. Yeah, that was enough. We'll proceed now. So yeah, available is a vector of length m, where m is the number of resource types. Then every value indicates the number of instances available of that type. So if you have 3 monitors, 2 processors, 1 printer, your available will be a vector containing 3 to 1. This we saw in the safety algorithm also. Max is an n cross m matrix, n being the number of processes or threads, m being the number of resource types. It defines the maximum demand of each thread. So this is the additional information we assumed will be given to us for deadlock avoidance, right? What is the maximum amount of this resource type that this process can ask for? If you remember, when we started out, we saw here, each thread declare the maximum number of resources of each type that it may need. So that is what we are being given in this max. So if max of I of j equals k, it means the process pi or the thread ti cannot ask for any more than k instances of resource type j. So at max, ti can ask for k instances of j. So if max of 0 of 3 equals 5, then process 0 can ask for at most 5 instances of resource type 3. That is max. Allocation, again n cross m matrix, defines number of resources of each type currently allocated. So what has been currently given to the process. Need is what more can it ask for. So need is max minus allocation. So there's nothing much to explain here. Max is for every process, for every resource type, at most how many instances can I ask for. Allocation is how many instances have I currently been assigned. Need is how many more can I ask for. So it is obviously max minus allocation. All three of these are n cross m matrices, right? So this is the data we are initializing. Next, our algorithm. We first quickly look at the safety algorithm. Work is equal to available, finish is equal to false. It's the same steps. If you look at it, this is the exact same steps which we went through in the safety algorithm for deadlock detection. There is no change at all. You find an index such that finish is equal to false and need less than equal to work. So in back there they called it request, here they're calling it need, which is the same thing. How much more this process is going to ask for. It's just different names, different terminology. So if you find an index like that, work is equal to work plus allocation, finish is equal to true, you will keep looping steps 2 and 3. When you no longer find such an index, you break the loop, you go check the array finish. If everything is true, it means you've done, you are in a safe state, you have the safe sequence. If not, some task is unfinished but you're not able to find a task which fulfills these conditions, it means you are in an unsafe state, right? This is exactly what we saw there. So this algorithm is there. Let's keep this in mind. Where do we apply this in this context? We will see soon. Right. Now, so this is where we are actually going to look at the banker's algorithm. So let's take a look. So let me clarify here that all of this initialization which we did and this safety algorithm, it is just there. So you first initialize everything and then you're not running the safety algorithm, it is just there. You know that this thing is defined as such. Now your algorithm actually starts over here. So if request less than equal to need, go to step 2. So you have your processes, right? T0, T1, so on. So you will start as usual with T0, you will go sequentially. You will see whether request less than equal to need. Now, yeah, so what is request? Request is the amount of resources that this process is asking for, right? Request also, if you remember, we saw in the safety algorithm as well. So if a process is asking for 1 unit of resource A, 0 units of resource B and 3 units of resource C, then the request corresponding to that process will be 103. Now you will first check whether request less than equal to need. What is need? Need is the maximum number of resources this process can ask for. Maximum as in it cannot ask for any more than this. So like this process said, I will need at most this many instances of these types that was defined in max. From that it already has a certain number of instances. So the remaining is what you can at most give it, right? So let's say this process said I will need at most 7 printers. Now you have already given it 3 printers, meaning it can request for up to 4 more printers. It cannot ask for any more than 4 printers now, correct? So that is what we mean. So request is the number of printers it is asking for and need is the limit on how much more it is allowed to ask. So obviously request should be less than equal to need. Whatever you are asking for should be less than equal to what you are allowed to ask for. If yes, proceed to step 2. Otherwise, raise an error condition, because you've been told this is the maximum I can give you, but you are asking for more than that. So that is an error. So if request is greater than need, you will raise an error. If request is less than equal to need, you go to the second step. Again, second step, you will check if request less than equal to available. This is very similar to what we did in the safety algorithm. This process is asking for this much. In my inventory, I have this much. Is the request less than equal to what I have? Can I fulfill this process's request using what I currently have? If yes, go to step 3. If not, this process cannot be executed right now. So you will move to the next process. Right. So assuming this was true and you come to step 3, what you will do is we will pretend to allocate the request and we will see what happens. So available is available minus request. So whatever I have, from that I am subtracting what was asked. Allocation is allocation plus request. So whatever that process was allocated, to that I am adding this. So from my inventory I am taking out whatever was requested, and to that process's allocation I am adding that. And need is equal to need minus request. Again, this is important. So this process, we will go back to this example. This process said it needs maximum 7 printers. Already I had given 3 printers. Now it requested me for 2 more printers, right? So now that request I am allocating. So my allocation becomes 3 plus 2 is 5. Now my need should become 4 minus 2 is 2, right? Because max should be allocation plus need, or need should be max minus allocation. So that relation should always hold true, meaning if you are allocating some extra, then what the process is allowed to ask for is going to reduce, right? So to give you a simple analogy, let's say you have a fixed pocket money of some 1000 rupees per month, which is what your parents are ready to give you, which you generally get, let's say, on the 30th of every month. But this particular month, for some reason, you need some money beforehand. So you're requesting your parents on the 10th date to give you some 500 rupees, which they give you, meaning on the 30th, the maximum money you can receive from your parents now is the remaining 500 rupees, right? So if they are allocating something to you beforehand, then from what you are allowed to request in future, something is going to go down. That's what is happening here. So from my inventory, I'm taking something out. To your inventory, to what has been allocated to you, I'm adding that. So what you are now allowed to ask me for is going to reduce. So we will modify this accordingly, and then whatever matrices you have, on them you will run this safety algorithm. So you will run the safety algorithm, you will see if there is a safe sequence or not. If there is a safe sequence, well and good, this allocation was fine, this process executed, I'll go to the next process. We did this for one process, remember we did this, let's say for T0, I'll move to T1. I'll assume T0 has been done, I'll move to T1. If I do this and I run the safety algorithm, and the safety algorithm says, no, there is no safe sequence, this system is unsafe, then I will undo all of this. So I will, whatever I subtracted from need, I will add it again. Whatever I added here, I will subtract. Whatever I subtracted here, I will add it back. So I'll bring all these three back to their original position. So I am basically undoing everything. And then it means if I allocate whatever this process is asking me for, I am putting my system in an unsafe state. So I cannot allocate. That is what we mean, right? So however the new state is unstable, then Ti must wait. So the old state is restored. Then you go to the next, so T0, let's say, led to an unsafe state. So you will undo all of this. So T0 cannot execute now. You will move to T1. You will do the same thing for T1. Check the safety algorithm. If that is safe, well and good. If not, move to T2 and so on and so forth. Right. So I'll give you a quick recap of the algorithm. In the next segment, we'll solve an example. It should make more sense. So yeah, this algorithm is used for deadlock avoidance when you have multiple instances of the same resource type. You are initializing some variables here available, a vector of length m, where m is the number of different types of resources you have. Every value indicates of that type of resource how many instances I have. Maximum is an n cross m matrix. N is the number of threads, m is the number of resource types. So every thread, every resource type, what is the maximum number of instances I will need? Allocation is how many of those instances currently are with me. Need, how many more am I allowed to ask? So need is maximum minus allocation. Cool. And we have this safety algorithm at hand, which is the same as what we discussed in deadlock detection. So with all this in hand, how we proceed? We proceed step by step, that is one process after the other, P0, P1, P2, P3, P4 and so on. So we take the first process, we check whether request less than equal to need. Request is the amount it is currently asking for. Need is the maximum amount it is further allowed to ask for. So there was one maximum that it is allowed to use, from which some part has been allocated. So the remaining part is what is need. So you check if request less than equal to need. If it is not the case, this is an error. It is asking more than it is allowed to use. You're allowed only 1000 rupees and you're asking for some 1200. So that will raise an error condition. If that is not the case, if request is less than equal to need, very good, move to step 2. Is request less than equal to available? You're requesting something. Is it available with me? You're asking for, let's say, 1000 rupees. Do your parents have enough in hand to be able to give you that 1000? If not, you must wait. Your parents will tell you, I don't have that much right now. Once I get some more, I'll give it to you. So you will make that process wait. You will move to the next step. Supposing there is enough available in your inventory to meet the request, you will allocate the request by taking something out from your inventory, giving it to this process, and accordingly adjusting the future demand it is allowed to make. So you will make these adjustments, then run the safety algorithm with that data. So once you have made these adjustments, you have a new value for available, for allocation, for request, right? So using those values, you will run this safety algorithm. If you get a safe sequence, well and good, proceed to the next process over here. Come back here and proceed to the next process. You assume P0 is fine, it's not causing me any problem, P0 is done, move to P1, or P1 is done, move to P2. If you run the safety algorithm here and it says there is no safe sequence, this is an unsafe state, then come back, undo everything that you did here. So simply reverse this wherever you did a minus, do a plus, and vice versa. Reverse these three. So basically, see, we tried allocating some resources, we checked if it was safe. If it is safe, we're just moving on. If we realize that it is not safe, then we're going to take back the resources, right? So that's, it's like your parents gave you money once, they wanted to see if you're spending it in the right way or not. If they see that you are not using it the right way, they're going to ask you to give them back the money, and from next time they're not going to be giving you that kind of a thing. So you take back whatever you gave, and then you say P0, please wait, I cannot handle your request right now. You move to P1, P2, and so on. So that is how you avoid a deadlock, by not allocating if it leads to an unsafe state. So that is the banker's algorithm. The next segment we'll see an example.